I2c and the very similar SM bus are in almost everything. You'll even find it as a major part of computer motherboards. The interface allows communication with up to 127 devices with only 2 wires. For many sensors, I2c is the standard way to get data. So here we have 2 wires, and you've got the S clock and the S data. That's SCL and SDA. The reason that the bus can communicate with 127 devices on only 2 wires is because those wires are open drain. Open drain means that the driving side only drives low. Each of the wires have to have a pull-up, which means that when the line isn't being driven low, it gets pulled high. Now, if you see a schematic one day and you see 2 resistors pulling up to the power rail, you'll know why that is. The value of these resistors can vary quite a lot, and that depends on the speed grade of the interface. The smaller the resistance, the faster the response. I2c is a really slow interface, and a comparable one would be dial-up internet. Dial-up internet was like 56 kilobits per second. I2c's lowest standard speed is 100 kilobits per second, so its standard speed is double the speed of dial-up internet. Now, a gigabit internet connection, for example, is over 10,000 times that speed. I2c until recently only had 4 speed grades, but in 2012 a 5th one was introduced. These speed grades might not be good enough for things like internet or displays, but they are ample for most sensors and data acquisition applications. The sample rate of common sensors, especially mechanical ones, is mostly quite slow. Strain gauges, which are on bridges, only require a few hertz for the sample rate. Even accelerometers rarely go above tens of kilohertz, and the I2c bus in the megabit range easily accommodates the data requirements for those sensors. Now, if we have an accelerometer that samples at 32 kilohertz, which is unrealistic, we only need 256 kilobits per second for an 8-bit accelerometer. Every sample of an 8-bit accelerometer requires 8 bits of data to communicate, so multiplying the speed, the sample rate of the accelerometer with the bits, you get 256 kilobits per second. Let's assume that half our frame is our data and the other half is the address, and so for this case it would be 512 kilobits per second, which is far below the 1 megabit per second mode. Now, even with our unrealistic accelerometer, we're still okay with 1 megabit per second. So every transaction begins with a start condition. The start condition is when the data line gets pulled low and then the clock line gets pulled low. After the start condition, data is sent. The data that is sent is usually in 8-bit blocks. Each of the 8 bits is sent with a rising and falling edge of the clock. This is called clocking out data. In the case that it's a read transaction, you would be clocking in data. The master still drives the clock, but it doesn't drive the data line. After the block is complete, there are 2 different things that can happen. If the slave device is okay with the data that was sent, then it will acknowledge the transaction and it will pull the line low. If it's not okay, it will allow the line to float high, which indicates that there's a problem with the transaction. The first block of data that is transmitted is the address of the slave. The address is between 0 and 127, and this is a 7-bit address. There are another type of address, this is 10-bit addresses, but we're not going to talk about them here. If a device exists on the I2c bus with the address that was sent, then an acknowledgement will be received. That's when the line is pulled low. If there isn't a device with the address that was sent, then the acknowledge line will stay high. Now, there are some devices that claim to have 8-bit addresses, but this is usually a device that says it has 2 different addresses, where the read address is this and the write address is that. Notice that the least significant bit is the only thing that changes in these addresses. This effectively means that even though they say it's an 8-bit address, it's actually a 7-bit address. You can take the version of the 8-bit address and say it is the 7-bit address. After the address is sent, depending on what the read and write bit was, data is either received or it is sent from the microcontroller. If the read-write bit was 1, then the master is receiving data. If it was 0, then the master is sending data. When the master is receiving data, it just leaves the data line alone and allows the slave device to set the data bits. If the data block is not acknowledged by the slave, then it's probably the slave saying, "Stop reading, there's no more data." If the master was writing data and the slave didn't acknowledge, then there's a problem. If all went well the master will probably then follow through with a stop condition. The stop condition is when the clock line is released or allowed to go high, and then the data line does the same. It is allowed to go high. Between blocks of data, for example, between the address and the data blocks, the clock line is held low, but the data line is allowed to go high. If you were bit banging this, for example, this makes things quite simple because your function that writes data only needs to clock out 8 bits of data and before and after the transaction have a start and stop condition. At the end of data sending, it's always required that the data line is released for acknowledgement, so the state between data blocks is always going to be okay. I've always found it very useful to learn how to bit bang algorithms so that you fully understand it. So we're going to do that right now. We're going to bit bang the algorithm. So here we go. Okay, so we're just going to put it in C++. The code I'm working on here is based on the example for bit banging SPI. I use some structures which help in developing these bit banging libraries. I'm just going to work on the bit banging library now. This is a simple implementation and a lot of it is based on the previous SPI bit banging tutorial. So the first thing I'm going to do is write this send function. The send function is a basic for loop which sends 8 bits, and this is going to be the fundamental thing that sends the address and the data and all that kind of thing. So the send function is basically just a loop, and it does a few different things, and it accesses, GPIO through functions instead of actual pin, set, and clear calls. The reason that we're doing functions instead of direct pin, set, and clears is because the functions kind of isolate the platform agnosticism. So that if I were to change platform from this Visual Studio environment to, for example, MSP430, I would only have to change the code inside those functions. So I can have those functions in their own file, and that file just includes everything that is platform dependent. So I'm just modifying the SPI code, just make the names and logging system make any sense. The way I actually do this is by having before and after any change of a pin, I basically just record the state of all the pins. And that's all I'm doing here. That allows me to plot the data and see kind of like the relative change between each of the pins, assuming that there's no noticeable overhead from program execution. Okay, in the send function, we're just going to store it temporarily. We're going to mask out that top bit, and we're going to store the temporary and probably like clock it out. Clocking out is the rising and falling edge, so let's write that. Okay, so a rising edge is setting it high, then a falling edge is setting it low again. Okay, so we need a start and a stop function, and those just assert the start and the stop conditions we talked about before. Those are going to be used in the I2c write, and the first thing we're going to do in that function is assert the start condition. Then we're going to send the address, of course, and then the data, and then we're going to assert the stop condition. In between each of the blocks of data we send, we're going to look for an acknowledgement. So we need a function that converts an 7-bit address to the 8-bit data address, and that function is going to take whether it's a read or a write address, and that read and write is the lowest bit of a byte. So all we're going to do is mask the address to make sure it really is 7 bits, then we're going to shift it across so we have room for that read or write bit, and then we're going to OR in that bit. We also need a function to get an acknowledgement, and an acknowledgement is basically allowing the data line to go high and then clocking and reading the data from the slave, and that's what we have here. Now if we don't receive an acknowledgement, we do want to abort the write routine, so let's check if we received an acknowledgement and then figure out what we're going to do with that. I think I'll probably just return true if it's successful and false if it's not. Okay, so I've got to make sure that I'm actually setting the output. That's the SDA, so let's call a function that gets that bit out temporary and sets the pin. Okay, so we're going to write to device OX10 and we're going to write the data 81 in hex. So we should see that in the spreadsheet we're going to generate. I need to make sure that the default states of all the pins are correct. So they've got to be all default high because by default the bus is open, it's open drain. Just going to update the write routine so that it does indeed stop if it receives the acknowledgement, it sends the stop condition. I mean, it should probably do that anyway, but it doesn't matter. Okay, so now it's fixed. So what I'm doing here is just setting the default state of the pins in the variable so that it's also defaulted to 0 on the actual variables. And then what I'm doing here is just copying the values from the terminal that it output to. The I2c print command did that. Okay, so I've got a scatterplot and librecalc here, and let's just check it. Here's the start condition, and here we have the address. There are 7 bits there, and here's the acknowledgement here, which we haven't received because we're not actually talking to a device. And the condition before the data byte is correct, so it seems like our formation of the frame is correct. Hope you learned a little bit about I2c. See you next time.